Okay, so welcome back. So what we have seen in the previous class, or I mean, whatever the morning session, is that we can make approximations. So these approximations are important because it helps us identify which terms, or if there are certain terms in the equations which are of small order of magnitude, and therefore they need not be carried forward and they can be dropped. Okay, and we saw that by picking up a characteristic velocity scale, characteristic length scale, and such things, we can non-dimensionalize the various terms, and that helps us identify. So then we said that depending on after non-dimensionalizing, my non-dimensional velocity is expected to be order 1. The gradients of velocity, whether it's first derivative or the second derivative, all of them are expected to be of order 1. Okay, and therefore the coefficients which are sitting in front of it, which are our non-dimensional numbers like Reynolds number, Froude number, or Euler number, those are the numbers that start determining whether that term is going to be important or not. So that makes it pretty straightforward to look at the non-dimensional numbers, and that's why we just look at the non-dimensional numbers and we decide which terms to keep or not. So that's the whole process that was illustrated in the previous whatever happened before this. Now, then we looked at the two extreme cases of creeping flows where the initial terms are not important, which remove the non-linearity, which is where the difficulty lies, and allows the solution, so now we get a linear equation, which means that the solution can be superimposed. I can take two different problems, and if the problem is such that it is combining the two conditions, then the solution will be simply a sum of these two solutions. Okay, and an example of that you saw in the mid-sim, where we had like a plate which is driving the flow. There is also a pressure gradient which is driving the flow. So there is a quick flow and there is a Poiseuille flow, and the solution is essentially a sum of these two solutions because the initial terms was not there in a fully developed channel flow. So that's basically what you get in the case of a linear equation. Now the other extreme that we saw is when the Reynolds number becomes very large and the viscous terms are effectively not important. It's not that they will not be very important, they will become important in a certain region, which is a boundary layer. Okay, and that's what we are going to see now, or in more detail. We'll do an analysis of the boundary layer. But assuming that that applies, as a flow is totally inviscid, we saw that the viscous terms are lost, which means that the second order terms are no longer present, and therefore we have to prescribe one less boundary condition. We have to allow for the flow to slip at the surface. The non-penetrative boundary condition, that still needs to be retained, but the no slip condition is where the relaxation has to happen now. And we saw the consequence of that if you were to have an object in the flow, like a cylinder, which is a two-dimensional cylinder which is placed in the flow, then we will see that because there is no viscous effect, there is no, or at least we are saying that there is absolutely no viscous effect. Okay, there is going to be pressure on the front side and the pressure on the back side are exactly the same. That means that this object should not experience any drag. Okay, and the drag happens because we saw that there is a pressure recovery that should happen. Complete pressure recovery, if does not happen, then the boundary layer separates, and then we get into a mess. We have a wake which is large, or a large size, which starts contributing to a form drag. So that's essentially what we get there. In the case of the low Reynolds number flow, we found that the flow is very attached and the pressure on the two sides are not the same because of the viscous effect, and that leads to a net drag on this object. Okay, so this is what we had looked at. So now we will look at boundary layer, and we'll start looking at it in more details. So boundary layer over a flat plate. So let us consider that there is a flat plate or a surface which is exposed to the flow. So there is some uniform flow, let us say, let us just keep it as capital U, which is coming and hitting this plate. This is my x direction, this is my y direction. I assume that the plate is very long. And as we know that there will be a boundary layer which will develop. Now, what exactly is a boundary layer? The boundary layer means that at the surface, we know that the no-slip boundary condition has to be satisfied. The flow will go to zero velocity here. There is going to be a velocity of capital U, which is far away from this surface. And therefore, there should be some gradient, which is taking me from zero, which is here, to some loss, this finite velocity, capital U, far away from the plate. So this is how the velocity distribution would be. So we call this as the velocity profile. And it is obvious that as we keep going further into the flow, my velocity profile or the boundary layer thickness or the region which is being experienced. So boundary layer thickness is the region which is experiencing this gradient. And I will start to see that as you keep on moving along the x direction, the boundary layer thickness will start to increase. So if I were to do an analysis of this, maybe we can start saying that these are my governing equations. So here we will be interested in finding out what is the equation of this boundary layer. Okay, so that is what we would like to drive. So we know that we have the continuity equation and the momentum equation, which are there. So we're writing it out in 2D, and we are saying that the flow is steady, so we have removed the unsteady term from the equation. So these are my equation that we have. So obviously these equations are very involved. They are involving three variables, u, v, and t, and we have three equations. If we have a closed system, that is not an issue. But these are a very complicated set of equations, and it is not possible to solve these equations analytically. So what we are going to do is what we did earlier, which was to see if there are certain terms that can be removed from these equations. Okay, so and we are going to use the process of non-dimensionalizing to help identify if certain terms can be removed. So maybe because you would have seen, have you seen boundary layers earlier? I mean, have you done an analysis of boundary layers before? Yes, no? Yes, good, okay. So what is the first step that you do? Non-dimensionalizing, scaling analysis. So what is the difference between the scaling analysis that we just did versus whatever we are going to do with boundary layers? Yeah, that's the key difference. So what is the key difference is that we are going to use two different length scale along the x direction and along the y direction. So earlier in the previous case, we had taken the same length scale. Okay, we said everything x and y are non-dimensionalizing with L0, and that allowed us to write x star and y star. Okay, but what was happening there is that all these viscous terms turns out to be of the same order, right? Because we have just seen that. Okay, so all the viscous terms are of the same order. So if that means that if one term needs to be dropped, everything else needs to be dropped. Okay, and that is not something which is applicable to a boundary layer. Okay, so what we are going to now do is to say that there are two different length scales. So we will use a length scale of L along this direction, and we will use a length scale of delta along this other direction. So X, characteristic length scale of along X, is capital L, and characteristic scale along Y is delta. Now, what is my characteristic velocity? Now, first let us look at the characteristic velocity. What is the characteristic velocity that I should use here? U, that is very clear. There is only one velocity that I have, and I should use that. Now, should I use this velocity along X or along Y direction? It's very clear that I should use it along the X direction. So let us say that this is along X is capital U. So the question arises, what is the characteristic velocity that I should use along the Y direction? Is it same or is it not same? Right, so now we have to see that I cannot pick up anything arbitrary. Why cannot not pick up anything arbitrary? Because you can see that the continuity equation that we have written has to be satisfied. Okay, so you can say that the first term that if you look at, it is U here, and then if the way that we were non-dimensionalizing, this is going to be L here, plus whatever is the V scale, I just put a V here for now, by delta, do V star, do Y star is equal to 0. Correct? So this is what I would get if by just looking at non-dimensionalizing the equation. The only difference now that we are doing is that we are non-dimensionalizing X with L, non-dimensionalizing Y with delta. Right? And that means we had already said that these two terms are of order 1, which means that the coefficient should be now equal. Why should they be equal? Of the same order? I mean, they should. Is because I may not equal in some sense, but of course this is all order of magnitude. So this is of order magnitude 1, and therefore these should be of order, same order. Okay, so that means that U by L is of the order of, if you want, as same as V by delta. So that means that V should be the order of, if you want, you can just write it as order of U times delta upon L. Okay, so maybe if you want to, before this, appreciate what is happening here. So let us say I take a constant Y line. So this is my constant Y line. This is where my Y is not changing. If I look at X along this, so if I look here versus if I look here, so it is very clear that here the point is outside the boundary layer, so the velocity here is U. Here it is inside the boundary layer, so the velocity is less than U. Correct? So that means that when I go from here to here, there is a dou U dou X. Correct? Similarly, if I keep on moving inside, I am moving to a region of lower and lower velocity, because I am effectively moving closer to the plate. Although I am not, distance is the same, but the viscous effect is going to become more and more dominant there as I keep going further down, and that means that effectively the velocity at this point should be less. Okay, so therefore my dou U dou X is now negative. Okay, which means that dou V dou Y has to be positive. Only then the continuity equation will be satisfied. and V is equal to 0 at the wall. So that means that V has to be positive to be able to make dou V dou Y as positive. Okay, so that means that velocity will always be outward in this case. V will be outward. But what we are also realizing is that V would have a very small magnitude. Okay, and how much is that? It would be like V by U. If you from here, maybe you can say V by U is like delta by L. So if the boundary layer thickness is very small, okay, as compared to, of course, the distance where we are looking at from with respect to the leading edge of the plate, okay, then the magnitude of V as compared to the magnitude of U, which will be much smaller, and of the order of delta by L. Okay, is this point clear first? Yes, no? Okay, so this is what I get. So I mean, we will just not use this order here. We will just say, okay, this is what I'm going to use. This is not approximately, just saying it's an order of. This is just a symbol that I'm using to say this is an order of. And I've already explained what order of means. We have to go to a log scale and then see the values. And yeah, in a certain range, we just say that it is of the same order. So you can see that that's the first information. That's the information that you have gotten from the continuity equation. We have gotten a very, very useful information. First, V is not 0, okay? And that is why a lot of things that were dropping off earlier are not going to drop off that easily, okay? But it is small. V is small. So next thing which we are going to do is to figure out the order of magnitude of the various terms which are involved in the x momentum equation. So in the y momentum equation. As we said, that always start off with the continuity equation, go to the y momentum equation, and then come to the x momentum equation. Just like what we had used for solving, we are going to follow the same order here as well. So we go to the y momentum equation and start looking at the order of magnitude of various terms. So U times dou V dou X. So what should it scale as? So you can see that this U is going to scale with capital U, right? This V should scale as U delta by L, and this X will scale as L. So this is 1 by L here. Now let us look at the other term, V dou Y. How should this scale? V is scaling as U delta upon L. U delta upon L. Same with this V, and this Y is going to scale as delta. So 1 upon delta U delta upon L. So this comes out as equal to U square, let us say, upon L. Let us say I will take that as common, into delta by L. And this is equal to U square, 1 delta cancels out, and I get by L times delta by L. Okay. So interestingly, what you find is that both these two convective terms are of the same order of magnitude. And this is something that we have seen repeatedly. Either both these two terms will stay in an equation or both of them will drop off. Okay. Even here, you can see that both of them are of the same order of magnitude. Okay, now let us look at the pressure term, 1 by rho dP dy. So this scales as 1 by rho. Now pressure typically scales as rho times u square. So that's what we will use, let us say, and then this is delta. So this is equal to u square upon L times L upon delta. So what we are trying to do is just keep one term u square upon L common in all of them, okay? So that we can then compare the remaining and then see what is happening, okay? So this is u square upon L. Although there is no L here, I have brought an L here, just so that I make this first term in first bracket term common across all the terms for ease in comparison. Now let us look at nu times d2v dx2. What about this term? Tell me. Nu v is going to scale as maybe 1 upon x. This is like x square will scale as L square. So let us do that first. And then this v is going to scale with u delta upon L. So let us again make u square upon L common. So I get in the second part a nu times nu upon u, okay, and L square is already here. So let us put an L here, one L here. So then what am I left with? A delta by L. I hope I have done this correctly. Right? Now what is my last term? Nu times dou 2v dou y2. How does this scale? Nu upon delta square and v, which is u delta upon L. This is equal to, okay, so let us just understand that, okay, one thing let me just point out in these equations, we are using an approximate here and equal to here, okay? You don't have to keep on putting an approximate because these two are exactly equal, okay? So these two are equal, but this is of order of this term here. So you don't keep on putting this tilde sign everywhere. Okay, it's only once that is required. Okay, now here what is this term? Again, let us make u square upon L common. U square upon L common. So I get nu upon capital U, and there is no, maybe let us put L here and L here. Is this correct? Something is not right here, as everything is. L here, L square. Sorry, tell me how much, what will you get here? L square, L by delta square. Now that's why something is not looking amiss here. Have we done things correctly? This is correct? Is this correct? Is this correct, first of all? Right? So if this is correct, then this should be equal to delta by L cubed. Is it? Delta by L. Let us see, if I write this, then okay, it's only delta by L. One delta is cancelling out, and then delta by L. No. Okay, should it be L by delta, other way around, right? Sorry. L by delta, maybe we should write it out. No, one delta is cancelling out. I think this is correct. So one delta is cancelling out, and this is what I get. Okay. So now, what was the purpose of this exercise? Let us remind ourselves. The purpose of this exercise is to figure out if there are certain terms which are small and therefore they can be dropped. Okay, so let me get rid of this equation now. so that there is no confusion. You have only these 5 terms in front of you. Okay, and you already said u square upon L is common. So you have to only look at the remaining part. So first term is delta by L here. This is L by delta. Okay, and then this is nu upon UL times delta by L. This is, so now what is this term here? Can you recognize this term? This is 1 upon RE. Okay, so the thing is that you are going to say that 1 by RE is going to become large. Okay, and therefore this is, it's very clear that RE is becoming large. Then this is 1 upon RE times delta by L. Delta by L is small, and this is 1 by RE times even smaller. Okay, so this term is the smallest term in the equation, and I can drop it off. Okay, and here, because of the same argument that delta by L is small, I'm going to drop off these 2 terms. Okay, and here when I look at it, unless and until L by delta is of the order of or larger than 1 upon RE, okay, I can drop off this term as well. Okay, so let us say that this is tentatively, maybe this I'm not very clear, not very convincing, so maybe I can come back and recheck my argument if this is correct or not. Okay, and you can see very clearly that pressure is L by delta times larger. This is now a larger term, and this term is going to stay. Okay, or if you want, if you are not convinced, maybe you can compare these 2 terms. So other terms you are able to make an argument, because this is 1 by RE times delta by L. No doubts here. This is also delta by L. This is delta by L. Now let us say that I am left with these 2 terms. I am not very clear. I can make this as 1. Okay, by multiplying it by delta by L. So then this becomes 1, and then this becomes just 1 upon RE, right? And then RE is large, and therefore this term can be dropped off. So there is no issues here, right? So then that means that everything in this Y momentum equation can be dropped other than the pressure term. So that means that my Y momentum's equation simply simplifies to dou P dou Y is equal to 0. Okay, so you can see that this simplification has given me a lot of information, which is that pressure is not going to be varying along the Y direction. Fine? Yes. Why does it scale? I mean, we had sort of seen that. I mean, we had seen in the previous case, I mean, I did not emphasize it enough. Okay, pressure we divided it by rho u square, right? And rho u square was essentially coming from the left hand side, right? So, and then we wrote it as Euler number. So this Euler number is typically taken as 1. Okay, and that's why the pressure difference always scales as rho u squared. So that's, I mean, if you sort of remember your static pressure, stagnation pressure, the difference between them is half rho u squared, right? So the pressure difference tends to scale as half rho u squared, other than when you go only when your initial terms are totally dropped off, and then we start scaling it with the viscous terms. That's what we did when we were looking at the creeping flow. Okay, otherwise pressure difference will scale as rho u squared. Okay, any other question?
Yes. Here are you making an assumption of high Reynolds?
Yeah, this is at reasonably high Reynolds number. Okay, so we are not assumption, but okay, we are looking at the flow where the Reynolds number is high. So in some sense, what we were saying earlier, in the inviscid flow, the flow will, I mean, the viscous terms can be totally dropped off. Now what we are saying is that region, there will always be a region where the viscosity will be important, viscous effects will be important, and therefore, and otherwise we will have to start applying the slip condition, which we know that it is not applicable, does not happen. The flow does not slip on the surface. So that means that something in our analysis has not been done correctly earlier. And that is when, because we decided to ignore the viscous terms altogether, whereas now we are saying that that is not exactly true. Okay. Other questions here before we move ahead? Yeah.
So for those 5 terms, first and second can be cancelled out, like in the y momentum. First and second can be cancelled out because delta by L is small.
Yeah.
Then third and fifth are compared and then said that it can be dropped out.
Let's see, if you want, I can actually maybe just multiply everything by L by delta first. Okay. L by delta first. So then this becomes a, no, sorry, maybe I should start from here. L by delta first. Sorry, delta by L first. Okay, so then this becomes 1. Okay, and then this becomes a square here, and this is also gone. This part is gone, right? So now it's very clear. This is delta by L square, this is delta by L square, times smaller than 1, which is just fine. I mean, this is delta by L. I mean, delta by L was small, the square of that is smaller still. Okay, so these two terms can be neglected. Okay, this term is also very obvious. It's also getting multiplied by RE, and this is also getting by RE. So as far as RE is large, okay, this term can be neglected. So it's a very clean argument. Nothing I have to recheck here. Okay. Any questions? Any other questions? So we have simplified the the y momentum equation. Now we start looking at the x momentum equation. So let us just get rid of everything, rewrite everything. It's okay. U do x. How does it scale? U square upon L, straightforward, right? V do U do Y. V is scaling as U delta by L. That's my V scaling. U scales as capital U and Y scales as delta. So this is equal to U square upon L. Same argument, same thing that we had said earlier. Convective terms will be typically of the same order of magnitude. Okay, just again taking a different example, different type of same order of magnitude we are getting. Okay, now we will take the case when the pressure has not been applied, so we will not consider this term. So this is without an imposed, let us make that statement, with no pressure gradient, with no imposed pressure gradient. So we are not imposing, that means that dP dx is equal to 0. We can impose pressure along the x direction. So here we are saying that there is no pressure gradient along the x direction, which is there in the flow. So I don't have to worry about the pressure gradient term at all. And then I go to the viscous terms. So how will this scale? Nu times upon L square times capital U, and nu times dou y2. This scales as nu times U upon delta square. So what do I get here? So again, I would like to make it in terms of U square upon L. So U square upon L. So this becomes nu upon UL, right? And this becomes equal to U square upon L times nu upon U delta or UL times L upon delta square. Okay. Now, how do I start making a comparison? Tell me. Okay, we can divide it like what you were saying. Otherwise, we can simply start comparing u square upon L. So this is u square upon L into 1, u square into L upon into 1. So I don't have to worry about the u square. I can just look at the remaining part, right? So this term is 1 upon Re, correct? So this term we can neglect, correct? Now what about this term? This is 1 upon Re. So now you can see that this term is equal to u square upon L times 1 upon Re multiplied by L upon delta square. So what do we do here? So now we start making the argument that, see, we have lost both the terms on the V momentum equation, and it was very convincing. Here, this is the smaller of the two terms, that is also very clear. This is L here, because here we have L squared sitting, here you have delta squared sitting. Okay, and delta is smaller than L. So this is very clear that this term is larger than this term. Okay, so this term is going to get neglected. So I'm only going to be, I'm left with one term. So that one term has to survive now. Okay, otherwise the viscous effect is going all together. Okay, is this argument clear? So now we are going to say that I cannot throw away this term, which means that 1 upon Re times L square upon delta square is of order 1. So that means that delta by L square is of order of 1 upon Re. Okay, or delta by L is the square root of Re to the power of half. So in some sense, you've gotten the scaling of delta right away. You know that boundary layer thickness grows as the square root of Reynolds number. Have you made a mistake in this? Yeah, this is correct, right? So we are already sort of saying that this is how the boundary layer thickness is supposed to vary. Okay, is this clear now? Maybe we should be very careful about Re also. What is the definition of Re that we have used here? Re, we have simply said it is nu UL upon nu. And because we can have Re based on that, so this is, we can just specify that this is based using length scale L. We can also have an Re based on delta, U delta upon nu. We can also define it like this. Because we have two length scales, I can define length scale with velocity multiplied by velocity and divided by nu. I can define it like this, or I can define it by like this. So there are two different Res now that I can have. So in order to differentiate or sort of be precise in telling that what Re are we looking at, I can put a subscript, let us say L in this case or delta in the other case, to make this point explicit. Okay? Any questions here? So what is the bottom line? That if you look at the x momentum equation, we are only dropping one term, which is this term here. Okay, every other term, these two convective terms, along with this one viscous terms, are going to stay. These three terms are going to stay. So that means my x momentum equation has now simplified to, so x momentum equation simplifies to u times dou u dou x plus v times dou u dou y is equal to nu times second derivative of u along y. Okay. So what is the complete set of equations that I need to solve from a boundary layers? Okay. First of all, everybody clear with, and let me again pause and see if there are questions. Yes. So we have already said that pressure gradient is, we are not imposing any pressure gradient. Okay. If there is a pressure gradient, then we can have other behavior that we will talk about later on. So you can have pressure gradient which is favorable, or we can have favorable or adverse pressure gradient. Okay, and we will see after, once we have looked at the case of zero pressure gradient. Yeah. What the plate is inclined, those are all more difficult cases. We're not considering those cases. Okay, anything else? So there's not a pressure driven flow. Yeah, what is driving the flow? It's just an inertia thing. Okay, so it's a uniform flow that has been created, and that is what is driving the things. So momentum driven, if you want to say. Okay, and we have in fact seen, in fact, you remember we just were talking about the pressure if it is actually in the other direction. So you can have a flow and you can have an adverse pressure gradient. Flow can always happen, even flow can happen in one direction, the pressure gradient can be in the adverse direction. We have seen examples of that. Flow around a cylinder, for example, we said that in the second part, from when the angle was varying from pi by 2 to pi, that is a scenario that we have. Okay, so the pressure is not the only driving force. Pressure driving force could be, it could be buoyancy, it could be gravity, okay, it could be surface tension. So it can be so many other type of forces could be there. It could be some body force like magnetic force which is driving the flow. Okay, so again, this is one sort of common thing. We only think of pressure as what is driving the flow. No, pressure is not always driving the flow. In the channel flow, it turned out that there is pressure force which is driving the flow and viscous force which is opposing it. And sometimes because we take it as the first problem, we only sometimes get fixated and say pressure is the only driving force. No, that's not true. Any other question? So what is my complete set of equations if I have to write it down? So we have our complete set of equations which are going to govern the flow of a boundary layer are dou u dou x plus dou v dou y is equal to 0. This is my continuity equation, this is my x momentum equation, and then the y momentum equation simply gives dou p dou y is equal to 0. So these are the three equations that we have, and again we are having it in three variables u, v, and p. Okay, earlier we had the same set, but now you can see that pressure is effectively not into the picture. Pressure is just a constant because pressure is not a function of x, not a function of y, it's just a constant throughout. And the other thing which happens is that, so there are effectively two equations in two variables u and v that we need to solve. Right? Maybe you can just think about what is the implication of this. So the implication of this is pressure P1, this is pressure P2. Here I'm just taking it as an example where pressure along the x direction need not be 0, because this is something that we have gotten and independent of what is pressure which is being imposed along the x direction. So this means that if this is a pressure which is here, then the pressure here outside along the same y, this is along the same y, pressure here will also be P1 and P2. So that means if you measure the pressure on the wall, okay, that is the corresponding pressure that you would have at these points in the flow. Okay, and other way around, if you impose certain pressures here, then that is the same pressure gradient. Whatever pressure gradient you impose here on the outside, the same pressure gradient is going to be seen at the wall. Okay, so it's actually quite an interesting and quite a useful result to have. Okay, and once we go along, we will see that we will have many other flows which will have this. Yeah. So we are saying that this need not be imposed, because I got this condition looking at the y momentum equation, which has nothing to do with whether dp dx is there or not. So if I am not imposing dp dx, so if this is the case, then p1, so if dp dx is equal to 0, then of course p1 is equal to p2. Okay, but I need not have dp dx is equal to 0. That's what I'm saying. Okay, is this clear? So now let us, before moving ahead, let us also look at what is happening in the outer region. So this is what is happening in the boundary layer region. What is happening in the outer region? The flow is inviscid, right? Why? We have already said it so many times. If the velocity gradients are 0, then there is no vorticity, right? It's an irrotational flow, and irrotational flows are inviscid. Nice result that we have already showed you. It's an incompressible flow, and it is irrotational, so it is inviscid, right? So that means what? And we have seen that we can simplify our Navier-Stokes equation to a Bernoulli equation, right? So let us start with the Bernoulli. Okay, so outside region, I can apply Bernoulli very easily. No issues there. No approximations involved. It's exactly applicable in the Bernoulli, in the outer region, right? So that means that, what will I say? P by rho plus u square upon 2, okay, plus gz if you want. And we have already said we don't bother about the gravitational effect, so we will not bother about it. To write it down is equal to constant. Okay, so that means that if I want to write out dp dx, I'm again saying that I can always put it for now and then worry about it later, whether I'm imposing it or not. Du dx is equal to 0. Right? So this is what I get. And that means that if I am not imposing any pressure gradient, which is the case that we are considering here, there will be no acceleration of the free stream velocity outside. Or if there is an acceleration of the free stream, it will give rise to a dp dx, which is essentially the case that we are not considering. Otherwise, if dp dx is equal to 0, if dp dx is equal to 0 implies that du dx is equal to 0. And the flow is not accelerating, flow is just constant. Okay, so this is the case essentially that we are considering. But what is important here is that to sort of realize and understand that the flow outside is inviscid. Okay, we can apply the Bernoulli equation there. Okay, and this relationship, simple relationship, applies. Okay, any questions here before moving ahead? Okay, so maybe before moving ahead, it's a good idea to prescribe what are the boundary conditions. So that we have a complete set of, governing equation as well as the boundary conditions before we move ahead and try to solve it. So how many boundary conditions do we need now in this case? I think we can look at this example and be very clear about it. So u along x direction, how many boundary conditions do we need? 1. Okay, u along the x direction. then u along the y direction 2, right, because of this term here. Then v along the x direction, not needed, right, because there is nothing that is involved. V along the y direction 1. Okay, so those are the 4 boundary conditions that we would need. Okay, so now what are the 4 boundary conditions? So u is equal to, so maybe u at y x at y is equal to 0, at all x's is equal to 0. Okay, if I want to, maybe greater than 0 if you want to be more clear, x is greater than 0 and all y is, sorry, and y is equal to 0, this is equal to 0, this is essentially corresponding to the plate, right? Then u, so along the y direction, so this is u along one point y is equal to 0 and maybe y at infinity, I can write it out, greater than 0, or I don't even need anything here, it could be anything, and y tends to infinity. This is capital U. So these are the 2 conditions that I have for u along the y direction, right? Now u along the x direction, so at x is equal to 0, I know, and all y's, or maybe y greater than 0. This is equal to, x is equal to 0 corresponds to this line here, and that is equal to capital U, right? And then v, for v I need along the y direction, right? V along the y direction, and what is that? Again, same as here, greater than 0 and y is equal to 0, v is equal to 0. This is my no slip, don't call it as no slip, no penetration. This is my no penetration boundary condition. Okay, this is your no slip boundary condition, no penetration boundary condition, and these 2 are my free stream conditions. Okay, so this is, and of course if you want to have pressure, okay, pressure along the y direction, so maybe we can say pressure at infinity, very far away from the plate, is equal to some specified pressure P naught or P reference or whatever. Okay, anyway, pressure is trivial because pressure is not varying along the x or y direction, so pressure is constant anywhere across the entire region of the flow. Okay, any questions again before moving ahead? So this is our problem statement. We have to, or this is the governing equation along with these boundary conditions needs to be solved. Okay, so how are we going to solve it? Yeah, so this is not trivial, so we will have to let us, so we will look for similarity, okay, that is one thing that we are going to do. Okay, similarity solution is still going to apply here because again there is no natural length scale in the problem. Okay, that's what I mean, or maybe it's not that straightforward because maybe there is a leading edge, etc. Okay, so there is a little bit of a issue there, but it turns out that the flow does exhibit self-similarity. And how do we know that? Ultimately, if you measure the velocity profile and you try to collapse them, there would be a way to collapse them using similarity variables. So you know that it exhibits self-similarity, and we would now try to look for that similar solution, self-similar solution. Okay. So I think what we will do, I think for today, I think we have had enough. Maybe we can stop here, and we will get into the details about finding the solution in the next class. So what we will do now is just look at the mid-sim. So